Good morning. This is going to be the last video for the normal curve, so it goes with your notes for 12.4C. And we're going to do normal curve and z-scores day 3. So we're going to take what we kind of talked about last time and then maybe apply it a little bit more. So remember, here's our z-score table. So we'll refer to that. So you're going to want to have a z-score table while you take these notes so you can know where I'm getting the numbers from. A survey indicates that for each trip to the supermarket, a shopper spends an average of 45 minutes with a standard deviation of 12. So there's our mean, here's our standard deviation. So standard deviation of 12 minutes at the store. The length of the time spent in the store are normally distributed. Find the probability that the shoppers will be in the store for between 24 and 54 minutes. So here's the picture we're looking for. And another picture might help a little bit. We're looking for, here's our standard deviation of 45, our average of 45. And we want to know between 24 and 54 minutes. So first I'm going to find what is 24 is down here. What's the probability that they will be in here or in the store for 24 minutes or less? So I'm going to find this right here, 24 minutes or less. So to do that, I'm going to find the z-score for 24. And remember, the z-score can be found by taking the x value, that 24, subtracting the mean, and then dividing it by the standard deviation. So it'll be 24 minus 45 divided by 12. And I get negative 1.75, which means that 24 is negative 1 3/4 to the left of the average. So it's negative 1.75 standard deviations away from the average to the left. So using my z-score table, go to the negative side and go to negative 1.7 and then over to 0.5. You should see it's 0.400401. So the z-score, the area under that curve there, right here, is 0.0401. So the area for 24, 0401. So that means that about 4% will stay in the store for 24 minutes or less. Then I'll find the z-score for 54 minutes. So the z-score for 54 minutes, I'm just going to do that over here. It'll be 54 minus 45 divided by 12. It'll be 9 over 12, so 0.75, which means that it is 0.75 standard deviations to the right of the average. So just about a full standard deviation. Then when I find my area for 54, that will give me how much is to the left, or what percent stay for 54 minutes or less. So looking at the z-score table, go down to 0.7 and then over to 5. So we're going down to 0.7 right here and then over to 5, and you got 7.7734. So 0.7734, did I say? Yeah. And that's the area or the percent of customers that will stay for 54 minutes or less. So now I need to figure out, so I know that 4% will stay for 24 minutes or less and 77% will stay for 54 minutes or less, but now I need to figure out the area between them. So what I'm going to do is take this bigger pink area and subtract off the green area. So I'm going to take the 0.7734 and subtract the 0.0401. That's going to give me 73333. So the probability that a shopper will be in the store for between 24 and 54 minutes is about 73.33% chance. Now we're going to interpret the answer. If 200 shoppers enter the store, how many, ask me for a number of shoppers, would you expect how many shoppers would you expect to be in the store between 24 and 54 minutes? So I'm asking you, what is 73.33% of 200 shoppers? So you take the decimal, and you multiply it by 200. So that's how you find a percent of a number. And I got 146.66 shoppers. So about how many shoppers? So I could say about 147 shoppers. You know, if I was looking for an exact number of shoppers that were going to be in the store, I might round down because I can't have 0.6 of a shopper. That doesn't make sense. But I was just looking for an approximate amount. So I was optimistic that the 0.6 would be an extra shopper. Okay, so same situation. Shoppers are spending an average of 45 minutes in the store with a standard deviation of 12 minutes. This time I want the probability that the shoppers will be in the store for more than 39 minutes. So we want to the right of 39 minutes, that area you can see in the picture here. So I'm going to find the z-score for 39 minutes, which means I'm going to take 39 minus the average of 45 and divide it by the standard deviation of 12. And for that decimal, I got negative 0.50. So if I look at my z-table and find negative 0.50, that's the first one here, negative 0.5, so 0.3085. So the area for that 39 is 3085. But let's look at the normal curve here. So the average is 45 minutes. So there's 50% on either side. Our z-score of negative 0.5 told me that 39 is half of a standard deviation to the left. And 0.3085 is the area below. So the 30% of shoppers, 30.85% of shoppers that stay in the store less than 39 minutes. So if I want to find the other side of it, how many are more than, so that's the one that fits our picture here, more than, you're going to have to remember that the whole thing is 100% or 1 minus that decimal. So you have to subtract it to find the other side here. And that'll equal 0.6915. Or 69.15% probability that they'll stay more than 69 minutes. Then interpret your answer if 200 shoppers enter the store. Well, then I want 69.15% of 200. Or I take the decimal, 0.6915, and multiply it by 200. And then I get, here I got 138.3, so I'm going to say it's approximately, I'm going to round down, 138 shoppers. Put 138 shoppers there. So for more than, you need to subtract your total from 1 because the z-score table always gives you the area to the left. So if you want the area to the right, you take it and subtract it from 1. IQ tests are sometimes used to measure a person's intellectual capacity at a particular time. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. If a person scores a 119 on an IQ test, how does this score compare with the scores of the general population? Okay, so let's take a look at, we have this normal curve and we have a average score of 100. If I find the z-score for 119, that'd be 119, subtract the average of 100, and divide it by a standard deviation of 15, I'm going to get 1.27. So 1.27 on my normal curve means that 119 is 1.27 standard deviations away from the average. So we're above the average. And if I want to know how far above the average we are, we can use our z-score table. So if I look at the z-score table and find 1.27, so go to 1.2, and I have to go over, so 1.2 is this one, 1.27 is right here, 0.8980. So the area for that was 0.8980, I believe. So that's this percent to the left here. So that means that this score, oops, spell score right, is 89.80% higher than the general population. Or this person scored 89.8% better than other people that took this test nationally. And then you could say, then use the other side of it and do 1 minus 0.8980. That would give you the 0.1020, or 10.2%. That's this right here. So only 10.2% of people or of the population score higher. So only, only 10.2% score higher than a 119. So it's a pretty good score. So if you're looking at your STAR scores and you see that percentile rank where it tells you, you are in the 54th percentile or you are in the 69th percentile, that is telling you where you are on the normal curve. So if you're above the 50, you're to the right of the average, or to the left of the average if you're under 50. And it tells you, and generally it'll say like 69%, you score better than 69% of your peers or your same grade level nationally. So it's a similar idea here. Kind of interesting to see where those numbers then come from. Okay, the ABC company is supposed to say produces bungee cords. When the manufacturing process is running well, the lengths of the bungee cords are produced normally. The lengths of the bungee cords produced are normally distributed, with a mean of 45.2 and a standard deviation of 1.3. Bungee cords that are shorter than 42 centimeters or longer than 48 centimeters are rejected by the quality control workers. So I want to use that information to find if 20,000 bungee cords are manufactured each day, how many would you expect the quality control workers to reject? So let's draw a little picture here. I have an average bungee cord length of 45.2. And then it says that bungee cords that are shorter than 42 centimeters, so 42 centimeters and shorter, that's to the left, those are rejected. And longer than 48 centimeters, so 48 centimeters, that's longer than, is to the right, are rejected by quality control. And then it's both of these percentages. So I'm going to have to find those two areas and then add them together. So first I'm going to find the z-score for 42 centimeters. So if I find z-score for 42, I'm going to take 42, subtract the average of 45.2, and divide it by 1.3 standard deviations. I'm going to get negative 2.46. Using my z-score table for 42, I'm going to look at negative 2.46, so negative 2.4, and then go over to 6, and it should be 0.0069. So that's this area right here is 0.0069, or 0.69% of bungee cords are rejected that are less than 42 centimeters. So then we do the same thing for z-score 48. So I do 48 minus 45.2 divided by 1.3, and I get a z-score of 2.15, which means it's 2.15 standard deviations to the right. If you look up the z-score area for 2.15, you're going to go 2.1 and then over to 0.5. and I got 0.9842. So 0.9842. But that is the area to the left. There's 98.42% of bungee cords that are less than 48 centimeters, not more than 48 centimeters. So if you want more than 48 centimeters to get this little piece, you do 1 minus 0.9842, and that's going to give you 0.0158. So that's the two percents. Now, if I want the total number, so I'm going to continue A down here. If I want the total number of bungee cords that are rejected, I'm going to add those 2% together. I'm going to find a total of 0.0227, or 2.27% of bungee cords are either smaller than 42 centimeters or longer than 48 are rejected. Now, 2.27 of 20,000 bungee cords, you're going to take that decimal and multiply it by 20,000. And we're going to get 454 bungee cords that are rejected. So that can be a quite a large amount, depending on how much it costs for each bungee cord. It could add up quickly. So think about what the company might do as a result of these findings. Are they going to maybe change how they're produced? Is it something that they need to tweak with their factory machines? How could they reduce the number of bungee cords that are being rejected? Okay, last example. This one we have to work backwards a little bit. So let's read it. Athletes should replace their running shoes before the shoes lose their ability to absorb shock. Running shoes lose their shock absorption after a mean distance of 640 kilometers with a standard deviation of 160 kilometers. Zach is an elite runner. He wants to replace his shoes at a distance only when 25% of people would replace their shoes. At what distance should he replace his shoes? So they gave me a lot of information here. They told me that the average distance was 640 kilometers that people replace their shoes, standard deviation of 160 kilometers. But Zach is an elite runner, and he wants to replace his shoes at a distance when only 25% of people replace their shoes. So we have to work backwards here. I was given the percent from the Z-score table. So use that to find what the Z-score was. So I'm going to look in the table, and 25% is to the left of the average because 50% is in the middle. So I'm going to want a negative Z-score. 25% is going to be to the left. So I'm going to look at my negative side of my Z-score, and I'm going to try to find where does it equal 25%. So I zoom out a little bit, and you look around here towards the bottom, you're getting close to 25%. Here's 26%, 25%, 25.78%, 25.46%, 25.14%, 24.83%. So the closest I can get to 25% is 25.14%. And that was negative 0.6 and 7. So my Z-score then for 25% was negative 0.67. So then remember, you have the Z-score formula, which says that you can take X minus the average divided by standard deviation. Well, X is what we're solving for here. X would be Zach's time, or the amount of miles that Zach would replace his shoes. So now I have now I have that negative 0.67 equals Zach's mileage minus the average divided by the standard deviation of 160. So now I can work backwards by multiplying by 160 to solve for X. So I got negative 107.2 here. It's X minus 640. Add 640 to each side. And we got 532.8 equals X. So he will replace his shoes at about 532.8 kilometers. Okay, that's it. Thanks, guys.